In the last class, we had ended up discussing how circular convolution equals linear convolution. And what we had said was basically that if you are given x1n of length L and x2n of length P, then this means that their convolution x3n, which is x1n convolved with x2n, has length of L plus P minus 1. And circular convolution equals linear convolution in terms of the output when the length of the circular convolution is bigger than the length of the linear convolution. So what we learned was if we compute x3p of n, which is equal to x1n, n-point circular convolution with x2n, then x3pn equals x3n if n is greater than or equal to L plus P minus 1. And that tells us a way of computing linear convolution using discrete Fourier transform. Because we already know circular convolution is equal to multiplication of the DFTs of those two sequences, and if you compute their inverse DFT. So x3pn, that can be computed as IDFT of, if I compute DFT of x1n, and I multiply that with DFT pointwise multiplication of x2n, and I compute the inverse DFT by the circular convolution, the relationship between circular convolution and DFT, this expression is equal. So that means that the linear convolution can be computed using DFT. So the procedure is simply that if you are given two sequences of this length, you compute n-point DFTs of x1n and x2n. So we compute x1 of k, which is n-point DFT of x1n. We compute x2 of k, which is again n-point DFT of x2n. Then in the next step, we compute another sequence x3 of k, which is simply x1 of k multiplied with x2 of k. And in the third step, we compute the inverse DFT of x3k. So compute inverse DFT, inverse n-point DFT of x3k to get x3p of n. And if the DFTs that we compute are such that the n, so if n is greater than or equal to L plus P minus 1, then this implies that x3p of n equals the linear convolution of x1n and x2n. So that is a simple way of computing linear convolution using DFTs. Now, why do that? Because although we haven't discussed it, we will discuss it in the next chapter, which is that DFT can be computed in a much faster fashion than computing linear convolution using its original formula. So if you think of the cost of, for example, linear convolution, so assume that L is approximately equal to P is approximately equal to capital N. Approximately means like it could be 2P, 2N, 3N, or so forth, right? Some constant times N. So this is what is known as, we are trying to do order analysis, which is sort of a common way of describing the complexity. How long does it take for an algorithm to run? Okay. So if this is the expression, then linear convolution, if you use the summation formula of linear convolution, okay, then linear convolution has a complexity of order n squared. Linear convolution requires approximately order n squared computations. And by computation, I mean multiplication and addition. Okay. So order n squared means that if I increase n by a factor of, let's say, 3, then the amount of time it is taking you to compute your linear convolution will become sort of 9 times. So it will become 3 squared. Right? The absolute constant, the absolute value, of course, will depend upon how someone coded it, what kind of a computer you were using to do that. Were you using a 1990s computer, or were you using sort of a supercomputer? But in order analysis, the main thing is that whatever is the system and the software and whatever you are doing, if you fix that, and if you increase now the length of your sequence, if you make n become 4 times or 5 times, the new amount of time that you would require to compute that algorithm is going to be square of that new length. So if you make it double, if n becomes double, you will require 4 times the amount of time. Right? If you make it 10 times, you will require 100 times the amount of time. So square relationships are really bad in terms of computations. Okay? But it turns out that DFT can be, if you use DFT as in its original form using the formula, then actually DFT also has order n squared complexity. But if DFT, you use these fancy algorithms which are called collectively fast Fourier transform, which is not really a transform but a way of computing DFT in a faster fashion. So DFT can be computed in order n log n to the base 2 operations. So operations, computations, or time, they are synonymous at some level. Okay. So if you want to think of it, let's say that you had a length 100 sequence and it was taking you some time, and you double. So as an example, double n, right? Then linear convolution using the formula will require you to do 4 times the computation, which means it will take you 4 times as long as the original sequence. But the DFT, if you compute it using FFT, will only be n is just, there is a factor of 2, and then log of n times 2, log of 2n, right? So this log, of course, logarithm is much slower than just n, right? So log n, of course, is much smaller than n. So your time will be more than a little double, even using DFT, but it won't become 4 times. Okay, it will be a little bit bigger than 2 times. Similarly, if you do 10 times in ordinary linear convolution, your time will become 100 times the original time. But if you use DFT using FFT, your time will be just 10 times a small factor. So maybe like 15 times, 16 times, but not 100 times. So it's orders of magnitude faster if you think about doing linear convolution using FFT than doing it using the explicit expression. Okay, so if we are ever computing long, so for computing large linear convolutions, we always prefer to compute them using the DFT, let's call it, if you want to call it, trick. Right? But the key idea there is you can't use DFT matrix multiplication. You really have to use FFT, which are faster variants of doing DFT. Okay. So the next topic, which is the last topic of chapter 8 that we'll cover, is implementing LTI systems using the DFT. So since we know that we can compute linear convolution using DFT and LTI systems, if you have this AHN as the impulse response, you have YN input XN. So YN is simply given by convolution of XN and AHN, which means that we can compute, if we are trying to implement some LTI system inside a digital computer, we can simply use DFT or FFT to compute that convolution. Now the challenge in that processing is that DFT requires, before you can carry out this expression, you have to have the entire XN present with you. Right? Because the way it works is you take XN, you compute its Fourier transform. If you don't have the whole XN, you are not going to be able to compute the Fourier transform. So while you can do that, it is not a good idea for real-time processing. For example, let's say you're trying to process some speech signal, which is inside you're trying to transmit it over a radio station, that before that you want to do some processing. Now, if someone is speaking, that means you have to wait for that person to finish speaking before you can start even processing that signal. That is infeasible, of course, because you can't wait for 2 or 3 minutes, or maybe someone is speaking for 10 minutes before you do that processing. Okay? So for doing LTI implementation in real time using DFT, we have to basically apply what is known as block processing. So for real time processing, of LTI systems, we want to do block processing, which effectively means we divide our input into small chunks and then process each chunk using DFT, and then process those chunks appropriately so that we get the output as if we were doing the DFT on the whole sequence. Okay, and there are two methods for that which we will study. So we are going to look at those two methods. The general principle is that we effectively divide our signal, which could be of infinite length, into small blocks. Then we process each block separately. But that is not enough. We really have to sort of stitch together the processed blocks in the right way. Otherwise, your output won't be the right output. Okay? So the main assumption we are going to make in this block processing is we'll say that our AHN is of length P, and our XN is of some length that is much, much bigger than P. Okay? It could be of infinite length signal. Of course, in reality, that won't happen, but we don't care what length it is, just that it is much bigger than the length of the filter that you are going to use. So the first method, which is called overlap and add, effectively takes your signal and divides it into non-overlapping chunks. Okay, so it divides xn into blocks of length L each, where each block is non-overlapping. Now this L is a problem parameter that you get to choose based upon how much delay you want in your processing. Okay, and you also want it at a level where using DFT really gives you an advantage. So while you can make this L to be, let's say, 1,000 or 50,000, but the longer the L is, that means the longer you have to wait before you can produce an output. So L is effectively a surrogate for how much is the delay between someone is inputting and you are obtaining the output. On the other hand, if L is too small, if L is like 1, then you don't really have any advantage as far as using DFT goes. Right? So you really want to pick the L in the right fashion so that you obtain the speed up of DFT or FFT effectively. Okay. So you divide this into chunks and you write each chunk as xrn. So you can write your xn as r equal to 0. We are going to assume that every signal is going to start only at time 0. So it starts from 0. It could be infinite length signal xr of n minus rl. Okay, where this is one block of xn. Okay. So if you want to write xrn independently, xrn without the time shift, that is just that block shifted to the 0 location. So that's just xn plus rl, where 0 is less than or equal to n is less than or equal to l minus 1 and 0 otherwise. Okay. So xrn is just the rth block shifted to the 0th location. So let's see. So here is an example where your AHN, this is of length P. It is reasonable but much smaller than xn. And effectively, you divide your xn into blocks of length L each. So you divide, if it is starting at 0, you divide, this is your first block up to L minus 1. Right? This is R equal to 0. Then you have your second block starting at L to 2L minus 1. This is R equal to 1. Then your third block, which starts from 2L and goes to 3L minus 1. This is R equal to 2, and so forth. Right? So just contiguous blocks, non-overlapping. So this one goes from 0 to L minus 1. The next block goes from L to 2L minus 1. The next one goes from 2L to 3L minus 1. And so forth. Okay? And then we define xrn to be this block shifted to 0. So we x0n, of course, is that block from 0 to L minus 1. x1n, so this is x0n. This is x1n. The only thing is we have just moved it to, instead of index L, we have moved it to index 0. Okay, it's exactly the same block. Similarly, we can think about this thing which has gotten hidden is x2n. Again, we have only moved it to the 0th location. So I can always write my signal into these non-overlapping pieces. So that is what overlap and add is doing. It basically waits for L samples, and then it processes them. Then it gets L more samples, it processes them. Then it gets L more samples, it processes them. And the question is, how, when it processes them, how does it add them together? Okay, and we'll see why you have to add them. So let's go back to then the formulation. So if my xn is written as this concatenation of these blocks, each of length L, then my yn, which is what I want, of course that is xn convolution with hn, but I can now I can write this xn in terms of the blocks. So I get r from 0 to infinity, x of r n minus rl, convolution with h of n. Okay. Now because of the linearity of convolution, I simply get r equal to 0 to infinity, x of r n minus rl, convolution with hn. Now what is this thing? This is basically convolution of a time-shifted version of xr with hn. Now by the LTI expression, so if I define yr of n as xr of n convolved with hn, then if I just shift my input by RL, then what happens to my output? The LTI property, my output gets shifted too. Right? So this is simply equal to r from 0 to infinity y of r n minus rl. Okay. So what is this saying? That your output is effectively equal to, just like your input was equal to sum of these pieces, your output can be written as sum of different pieces, where each piece is simply convolution of the input block with hn. Okay. But we have to be careful about one particular thing, which is that whereas xr's are of length L and you're shifting them by L amount. So you have one piece of length L, you have another piece of length L, there is no overlap between them. But what is the length of this yrn for each r? That is given by simply the convolution formula. So you have, this is of length P and this is of length L. So the output of this thing is of length L plus P minus 1. But you are shifting these pieces by only L, which is of course less than L plus P minus 1. So that means that if you want to produce the same output as if you are processing the whole thing together, you cannot say, let me take one block, linearly convolve it and output whole of it, and then take the other block and linearly convolve that. Rather, you really have to add those blocks after every L samples in the appropriate fashion. Okay. So what happens is that your yrn minus rl, this part, if you look at it, your first, let's focus on y0 and y1. Okay, y0 goes up to L plus P minus 1, and y1 starts at 0 and then you are shifting it by L. So y1 starts here somewhere at location L. This is y0, and then y1 is here. And to get the right output, you need to add these pieces together. There is an overlap between the previous y. There is an overlap between the output due to the previous input block and the output due to the current input block. If you want to get the right output, you really need to take care of this overlap. Okay? So every time you get a new block of input, the first P minus 1 samples need to be actually added to the last P minus 1 samples of the previous block's output. and only then you can produce the output such that the output reflects the right answer you are looking for. Okay, if you keep on just outputting y1n, y2n, then your answer won't be the correct answer. So let's take a look at it again in a pictorial fashion. So going back to the same example, we divided our input signal into these three pieces. Now, every time I get a new piece, I convolve it with my HN. So I get my first L samples, I convolve them, and I get Y0n, which is convolution of X0n and HN. So this is of length L plus P minus 1. It goes up to index L plus P minus 2. So the first L samples are fine. You get a new block, you output L samples. But the last P minus 1 samples, you hold on to them. You don't output them because you don't have the correct solution yet. Instead, now you take your next block, X1n, and you compute convolution of that with HN. So now you are now looking at R equals 1. Okay. If you want to produce your output for the first block, R equal 1, the first P minus 1 samples have to be added to the last P minus 1 samples of the previous block's output. So you add these samples of Y0n, the last P minus 1 samples. So you have from here to here, you have P minus 1 samples. Okay. You add those samples to these samples to get the P minus 1 samples. The next L plus P minus 1 samples are uncorrupted. You output them as it is. Okay. And then the last P minus 1 samples, again, you cannot output them. You have to now wait for the next block to be processed. So then you get your next block, which is X2n. You convolve that with HN. Okay. And now you take your P minus 1 samples of that output and the previous P minus 1 samples. And you output them and then so forth. Okay. So every time you get a new block of L samples, you go to your previous processed block. You always save their L minus 1 samples of the P minus 1 samples of that block. You add those P minus 1 samples of previous block and the P minus 1 samples of the new block. Then you output L plus P minus 1 samples as it is. And finally, you don't output the last P minus 1 samples till you get the new block of input. Okay? So that's why it's called overlap add, because even though your input is divided into these non-overlapping blocks, to get the right output, you really have to take care of these overlaps, which arise because of the fact that if you convolve length L and length P sequences, you get an output of length L plus P minus 1. Okay? So every L input samples produce L output samples. But the first P minus 1 part of those L output samples have to be computed using the previous block and the current block. And the last one of those samples, you just output them as it is. And then you hold on to the last piece. And it keeps on going. Okay? So let's write down in words the overlap add method for rth block. So r is any integer between 0 and whatever up to you run out of your samples. So while processing rth input block, we keep the previous output with us. We keep yr minus n with us. And we process rth block by computing yrn equals to xr of n convolved with hn. But we don't output this yrn. Rather than what we do is the first p minus 1 samples correspond to addition of first p minus 1 samples of yrn and last p minus 1 samples of yr minus 1n. Okay, so you get the new block. You output p minus 1 samples by taking the sum of your newest p minus 1 samples and the last p minus 1 samples of the previous block. Okay, so you compute that. Now the next L, so after that, the next L minus p minus 1 samples are uncorrupted. Okay, just as we saw in the previous version. So the next some samples will be uncorrupted and you output them as it is. So the next L minus p minus 1 samples are output as the next L minus p minus 1 samples of yrn. Okay, and then you stop. So in total you have output how many samples? You first output p minus 1 samples plus L minus p minus 1. So in total you have output L samples. You got L input samples, you output L output samples. But yrn still has p minus 1 samples left, and you hold on to them for now processing of the next block. Okay, so once you are in steady state in overlap add, every time you are producing L samples. When I say produce, I mean what you output. You're inside your digital system, you are producing, of course, L plus p minus 1. But you hold on to p minus 1 samples for the next block's processing. So in steady state, you get L input samples, you output L output samples. But how you produce those L output samples is really a function of the previous block and current block. So the first p minus 1 samples are sum. They are given by this overlap and add. The next L minus p minus 1 samples go out as it is. Your yr, each yr is of length. So yrn is of length L plus p minus 1. Okay. In steady state, you divide it into 3 pieces. The first piece is of length p minus 1. The last piece is of length p minus 1. And the middle piece is of length L minus p minus 1. Add them all up. L minus p minus 1 plus p minus 1, you get L plus p minus 1. So the total length is, of course, L plus p minus 1. While processing this block, you add this with yr minus 1 samples. Okay? This part gets output as it is. And then you hold on to this. You save this part or hold on to this till you get your next block processed. Okay? In steady state. as we talked about earlier, for the first block, this first version won't be there. And for the last block, the last overlap won't be there. Right? By there, I mean you don't have to worry about overlap there. But in general, in steady state, you have these three pieces of your output. The first piece gets added to the last pieces, last p minus 1 samples. The middle piece gets the output as it is, and then you hold on to the last piece, which is of length p minus 1, 2. Now, in addition to overlap and add, there is another method called overlap and save. So whereas overlap add works by dividing your signal into non-overlapping blocks, overlap save works by dividing xn into overlapping blocks. Whereas in overlap add, the output was produced by keeping track of two output blocks, yr minus 1n and yrn. In overlap save, you actually worry about your input. You keep track of different parts of your input, but your output simply gets generated without, you don't have to save anything for the output. Okay? And the way overlap save works is this. Remember, if we compute x1n circular convolution with x2n, and if n is less than or equal to L plus P minus 1. In fact, if n is strictly less than P, L plus P minus 1, then what happens? Your circular convolution is not equal to linear convolution, but what does that do? You get aliasing. We talked about circular convolution described by the aliasing, time domain aliasing of linear convolution. So if this happens, then the circular convolution is time aliased version of the linear convolution. And how is that linear aliasing described? We can say that x3pn, that is the principal period of, so one period of taking the linear convolution defined x3n minus rn. R from minus infinity to infinity. If you want to, hopefully everyone was able to do the reading assignment that we had discussed last week. So what effectively time aliasing of linear convolution is doing is it's taking the last piece of your linear convolution and just wrapping around at the beginning. Right? That's what aliasing is doing. If I look at, for example, if this is my, and I'm just drawing an envelope. So if this is my linear convolution, let's say, from 0 to L plus P minus 1, and if this is, let's say, L minus 1, so this is my linear convolution. And if I now do circular convolution with n equal to L, then what happens? In circular convolution, my output will be of length L, right? Because I'm computing n equals to L point circular convolution. So all these remaining pieces, this remaining piece, this p minus 1 samples, where would those samples go? those samples will simply be wrapped around and they will come here, right? You will have them wrapped around at the front. And so those p minus 1 samples will corrupt the first p minus 1 samples of your output. So this linear convolution, the first p minus 1 sample, if this is, let's say, if this was p minus 1, let me do another line here. Let's say if this was p minus 1, and these are p minus 1 samples, so these p minus 1 samples are going to get added to the first p minus 1 samples, and I will get some corrupted version of the first p minus 1 samples. This is due to aliasing. But after that, after those p minus 1 samples are gone, the remaining samples are going to be uncorrupted. So this is L minus 1, this is p minus 1. And of course, my output, my circular convolution output is always of length L, so I have only zeros after that. So what linear convolution is doing effectively is it's corrupting the first p minus 1 samples of your output. But the last, after p minus 1 samples, the output of these samples are the same as if you had done linear convolution. Okay, these are sort of uncorrupted samples. So the overlap add method is based upon that. It basically takes your signal and it does circular convolution instead of linear convolution. Now if you do circular convolution, your first few samples will be corrupted. So it throws away those samples, keeps the remaining L plus p, keeps the remaining L minus p minus 1 samples. Now the corrupted sample, it has to redo circular convolution. Okay, so because of that, it in overlap save, instead of dividing our signal into non-overlapping blocks, we have to divide our signal into overlapping blocks. I'll explain that a little more, but if mathematically, overlap and save divides xn. It still divides it into length of length L blocks. Okay, so it divides xn into length L blocks, but these blocks are overlapping. So these blocks are given by xrn equals to x of n plus r of L minus p plus 1 minus p plus 1 for 0 less than or equal to n less than or equal to L minus 1. Okay. Effectively, what this is saying is that instead of starting at RL, which was previously, if this was your sequence, I'm only drawing indices. Previously, you were dividing your sequence into, you started at L, 2L, 3L, and so forth. So this was your first block up to L minus 1. This was your second block up to 2L minus 1. And this was your third block. This is for overlap add. Okay. So in overlap add, we had non-overlapping blocks. In overlap save, we start by looking at p minus 1 sample before. Okay, we still have length L blocks, but we start by looking at, we always start a little bit behind. Okay, so we, instead of this, starting at 0, we'll start, for example, here. And similarly, we next go to L blocks, so we take L samples, but now the next block will start here, and so forth. Okay, we'll see a better picture of that in a moment. But mathematically, what this is saying is you divide your input signal into overlapping blocks now. You get L samples, then the next block, instead of starting after those L samples, start P minus 1 samples behind. And then it takes L samples. Then the next block starts P minus 1 samples behind and takes next L samples, and so forth. Okay? So you can expand this if this is for sort of overlapping blocks, and you can expand that, play with it a little bit to get a better handle on that. So this is an example where we have the same signal that we had for overlap and add. Okay? But whereas that signal was starting from, we were starting out taking samples at 0 location. In here we start a little bit behind that. Okay, we go P minus 1 samples back. So these are the P minus 1 samples back. Then in the next block, this is your next block, X1N. In overlap add, we started after the next block. In overlap save, we actually start with the last P minus 1 samples again. So we always start from P minus 1 samples behind where we ended. So we ended here in the previous version. We now start here, and we compute a length L block. Similarly, we go down. The next block we had ended here. So this is where we had ended, but instead of the next block starting here, we'll start the next block P minus 1 samples behind. Okay, so there is always this P minus 1 samples that we start behind the previous block where we ended the previous block. Okay, so now we are doing blocking of our signal, but in an overlapping fashion, which means every time I get L new samples, I process those L samples, but then I save P minus 1 samples or those input samples. So I get these L samples. I didn't throw away, after processing, I don't throw away all the samples. I save these samples. These samples are saved for the next block. Then I get more samples. I combine them to get a block of length L. Okay? And it keeps on going. Now, the idea in overlap save is then after you get these blocks, you do circular convolution with these blocks rather than linear convolution. And when we do circular convolution, the purpose of saving these previous samples become apparent, because what will be happening is we will be corrupting the first P minus 1 samples of our circular convolution, because circular convolution equals aliasing of my linear convolution. So I then throw away those samples, which means I have never computed their output. So I go and recompute their output again, and I keep on doing that. Okay? So mathematically, every time for a given R, XRN is made up of P minus 1 old samples of Xn and L minus P minus 1 new samples. Okay. So now you get these samples and you compute YRPN as a circular convolution of XRN, circular convolution of length L with HN. Now what happens because of this circular convolution is that the first P minus 1 sample of YRPN will be corrupted, right? So the first P minus 1 samples of YRPN will be time aliased, while the next L minus P minus 1 samples of YRPN will be equal to linear convolution of XRN and HN. Right? Remember, we are after linear convolution. But since we are doing now circular convolution, my first P minus 1 samples are going to be corrupted. So what I will do is I will just throw away those P minus 1 samples and keep the remaining L minus P minus 1 samples. Output those. Okay? But because of the fact that I have thrown away some samples, I now have to recompute my right linear convolution, which means I need to keep track of up to what point I have computed my linear convolution. And I have computed it up to the point of P minus 1 samples behind where I reached my input level. Okay, so that's why I always go back P minus 1 samples, redo the circular convolution, throw away first P minus 1 samples, output the next L minus P minus 1 samples, and then repeat this process. Okay, so mathematically what I want to do is I want to keep YRN equals to YRPN for P minus 1 less than or equal to N less than or equal to L minus 1, 0 otherwise. And then I output all of that. So my output is simply Yn equals R from R from 0 to infinity, YR of N minus R L minus P plus 1 plus P minus 1. Okay. So my output is not now all the block outputs. My output is always throwing away some portion of my block outputs and outputting the rest. So let's go back to this example. I first get L samples. Okay, those L samples actually for my original signal, those L samples correspond from minus P minus 1 to L minus P minus 1. Okay, so in my original signal, this was the 0th sample. Now I take this X0n and I compute YRPN equal to X0n circular convolution with HN. So let's use R equal to 0. And I get back this thing. This is my Y0PN. Okay. But the first P minus 1 samples of that are corrupted. They are not the right samples that we should be using. They are time aliased. Okay. Those samples actually came from the linear convolution, and that linear convolution got mapped to the first P minus 1 samples. So instead, we keep only these L minus P minus 1 samples. We output them. Okay. Now we go back to the next version. We get X1n and we compute Y1 P of n equal to X1n circular convolution with HN. We do this, again we are going back P minus 1 samples because the output of these, due to these samples, will be corrupted. So we go back, we get this output, the first P minus 1, this is again P minus 1 samples. We throw them away and output the next L minus P minus 1 samples. So the basic difference between overlap add and overlap save is in overlap add, you are using non-overlapping blocks of input, but your outputs blocks overlap and you have to add them up to get your answer. In overlap save, you divide your input signal into overlapping blocks. And by doing that, you don't have to now add your output blocks. All you have to do is throw away the first p minus 1 sample of your output and output the rest of the sample. Then you keep on doing that. Okay. This completes our discussion of chapter 8 for DFT. The basic idea I hope you get in terms of what is the relationship of DFT to DTFT. The rest of the stuff I'm pretty sure most of you have already seen in your undergraduate studies. And once you do the reading assignments for this lecture, you should be pretty much up to speed on that. In the next class, we'll start talking more formally about some aspects of chapter 9. We won't go into that much detail, but chapter 9 is about the fast Fourier transform. And although the name implies a transform, it's actually just FFT, or as fast Fourier transform is often called, is just a collection of algorithms for computing DFT. Okay, so FFT basically is a collection of algorithms for calculating DFT in order n log n to the base 2 computational steps. Okay. Remember, if you go back now to just the DFT, the way we started with, we said if you have a finite duration sequence of length n, we call it a vector, then your output x, let's say, which can be which is a n-dimensional complex number, that is equal to, let's say, this DFT matrix U times little x, right? So this DFT matrix was n by n, and this vector is n by 1. Okay, ages ago we started DFT discussion in terms of matrix vector multiplication. If you do DFT, if you compute the DFT coefficients using explicit matrix vector multiplication, then the cost of that is pretty high. In general, that will give the exact numbers, but that is in order n square operations, okay, which is as slow as linear convolution. So if you were to say, oh, I want to compute linear convolution using DFT, but if you use, for example, in MATLAB, you use DFT-MTX command to generate the matrix and then do matrix vector multiplication, it will be as slow as doing linear convolution. Whereas fast Fourier transform is a quick way of doing DFT, which basically does not explicitly compute the DFT coefficients. Okay. In the last 2 minutes of this class, let's just quickly go through explicit calculations of how much time it requires you to do DFT computations using this transform domain formula. Okay. Any n-dimensional transform, if you were to compute it using matrix vector multiplication, it will have this cost. But the good part about most transforms is that actually you can compute them in a much faster fashion than this. Wavelet transforms, DCT transforms, DFT transforms, they all can be done in much faster fashion than using this n squared operation. Okay, we use the matrix vector multiplication form because it helps us do the analysis, but in reality, in computation, you never do compute the transform by doing the matrix vector multiplication explicitly. Okay, so I'm not going to focus only on the DFT. You can compute that cost if you are given a matrix. So if you are given an n by n matrix, and let's call this the first row of that, let's call it U11, U12 up to U1n. And similarly, the last row you call UN1, UN2 up to UNN. And your vector is x1 up to xn. And you get your coefficients here, which is capital X1 up to capital Xn. Now for each coefficient, you are, to compute any coefficient, you are doing what? You are doing multiplying this row vector with this column vector, right? Simple linear algebra. So xi, that is simply equal to ui1 uik times xk, where k equals to 1 to n. Right? I've just written the formula for multiplication of a row vector with a column vector. Now if you look at this, and assuming that these things could be complex valued, so if you look at it, how many, for one coefficient calculation, how many multiplications are you doing? You are multiplying two numbers how many times? You have n multiplications. So for computing one coefficient using matrix vector multiplication, you have n multiplications and you have n minus 1 additions. Okay? And if these were complex valued, then to remind you, one complex multiplication, so if I write a plus jb times c plus jd, right, it involves how many real valued multiplications? It involves 4 multiplications. Similarly, one complex addition involves how many additions? Real valued additions? 2. A plus jb plus c plus jd, you have to add the reals and you have to add the complex. So you have 2 additions. So one complex multiplication involves 4 multiplications plus 2 additions. And then one complex addition involves 2 additions. So in general, if we have n multiplications for one coefficient, that means that we have 4n multiplications and if we have n minus 1 additions, then we have 2n minus 1 additions plus we have 2n further additions due to multiplications. Okay, so each operation in general involves 4n plus 2n plus 2 times n minus 1 operations for one coefficient. And now if you want to compute the amount it will take you to compute everything, that will be n times this number, okay, which ends up being order n squared. So you can compute the explicit constants too, but in general the point is that as the length of your vector increases, it doubles or triples, the amount of computations you have to do becomes a square in the length of your signal, which can be really bad as the length of your signal keeps on increasing. So FFT helps us go from this order n square to order n log n2, which is the focus of FFT-based algorithms. Now I want to make one more thing clear, that FFT is used to compute all coefficients of DFT in a fast fashion. If you are interested in only a few coefficients, then there are other algorithms that help you do that. Okay. This discussion of FFT, we are not going to look at all possible algorithms. We'll just look at decimation in time algorithm briefly, just to give you a sense. And after that, we'll move on to spectral analysis using DFT.